Good morning and welcome to Master Talker online class. In today's video, we'll be talking about gravitation, right? And the laws of gravitation. So the first one, we're talking about the Kepler's law. Okay, the Kepler's law stated that all planets moves in an elliptical orbit, having the sun as the focus. Okay, yes, all planet moves in elliptical orbits, having the sun as the what? The focus. Number two states that what? A line joining any planet to the sun sweeps out equal area in equal times. Okay, any line joining the planet to the sun, sorry, any line joining the planet to the sun sweeps equal area in equal times. Then the last one states that the square of the period of any planet about the sun is proportional to the cube of the planet's mean distance from the sun. Okay, that's the period, the square of the period is directly proportional to what? To the distance. Okay, to the distance of the is equal to the distance from the planet to the sun. Okay, so that is that. So the next one we'll be talking about, which is the main one, is the Newton's law of gravitation. Newton's law of gravitation. And Newton's law of gravitation stated that the force of attraction between two masses, m1 and m2, is directly, in fact, if you have two masses like this, if you have two masses m1 m2, and then this is their distance apart, he said that what? That the force of attraction between these two masses is directly proportional to the product of the masses, okay, and inversely proportional to the square of their distance apart. So if you now have that F is equal to, remove proportionality sign, you bring in a constant G m1 m2 over what? R squared. Okay, so now where your G is a constant and the constant is 6.67 times 10 raised by what? Minus 11. Okay, you need to know that is a constant in Newton meter squared per kg squared. Okay, Newton meter squared per kg squared. Okay, so that is that. So the next thing we'll talk about is let us get the dimension of this G. We have gotten the value of the G. So the dimension of G, if you have not watched my video on dimensional analysis, please do that. Okay, I solved it there, but let's just run it down. I know that my F is equal to what? G m all over what? R squared. Now, I now have that my G is what? Force. Force is equal to what? Mass times acceleration due to gravity is equal to what? G m over what? R squared. So one of these m will cancel one of this m. To make this G subject, I have that what? This is equal to G R squared all over what? M. Okay? So if you have that, you now see that what? That your G is measured in meter per second square. Okay? And meter per second square, meter, what gave us meter is length. Second is time. So since it is per second square, it will be -2. Then R is what? The distance. The distance. And distance is measured in what? In meter. What gives us meter is another L. But this L now is square. So I have square here. All over. This M is mass. Okay? And mass, what gives us mass is kg. And kg is what? Capital letter M for dimension. So if you bring this one up, you have what? M raised power -1. Then T raised power -2. Then L, 2 plus 1 is 3. L raised power what? 3. So this is the dimension of G, gravitational constant. This is the dimension of gravitational constant. Okay? So the next thing we'll talk about is the mass of the Earth. Mass of the Earth. Now, the mass of the Earth, let us calculate the mass of the Earth. We have that F is equal to what? F is equal to G, Gm, okay, let me say Gm m over what? R over R squared. But I know that force is mass times acceleration. So I have what? Mg is equal to what? Gm m over what? Let me change this to radius of the Earth, R squared. Okay, since I want to calculate the mass of the Earth, if this m will cancel this m now, I have that the capital letter M, which is what I'm looking for, the mass of the earth, will now be g(r squared) all over g. So if you put your value, you have that. You don't forget that g is what? Acceleration due to gravity, which is what? 9.8 times my r, radius of the earth is 6,400. Don't forget, all squared all over your g. We have gotten it before as 6.67 times 10 raised to power what? Minus 11. So if you do that, you will get that the mass of the earth is 5.997 times 10 raised to power what? 24. Yes, 24 kg. Okay, so this is the mass of the earth. It's a constant. You need to know that as well. So the next thing we'll calculate is the density of the earth. Let's calculate the density of the earth. The density of the earth. All right, you know the formula for density. Density is mass over volume. Density is equal to what? Mass over what? Volume. Okay, and I know they say that that the earth is spherical in shape. So the volume of a sphere is what? 4 over 3 pi r cube. Yes, 4 over 3 pi r cube. Okay, so if we now put it here to calculate our density, we have that what? That density is equal to what? Mass. The formula for mass we got is what? g(r squared) over g. Now divided by the volume we got is what? 4 over 3 pi big R cube, because we're talking about the radius of the earth. Okay, so let me put it 4 pi all over 3. So if I change division to multiplication, I'll be having g(r squared) all over capital letter G times 3 up here all over 4 pi r cube. Okay, 2 here we cancel 2 here, remaining 1 here. Okay, so what do I have? I have 3g over 4 pi g, 4 pi gr. Okay, so if you now put everybody, have 3 times 9.8, okay, all over them 4 times my pi is 3.142 times my g is 6.67 times 10 raised to power what? Minus 11. Then times the radius of the earth, 6,400. So if you do everything, permit me to finish it up here. If you do everything, you now see that the density of the earth will now be density of the earth is 5461.7 kilogram per meter cube. Okay, or 5.4617 gram per cm cube. So that is that. This is what the density of the earth. You can know that. All right, so the next thing we'll calculate, the next thing we'll move to what? The mass of the sun. The mass of the sun. The mass of the sun. All these things are constant. So if you don't know how to derive them, you can just cram the constant. Is a constant. But sometimes they will give it to you, sometimes they will not give it to you. So we have that our force is equal to what? Gmm all over what? R squared. Let me use R squared. Then in calculating the mass of the sun, we say that the mass of the sun, in fact, the force of attraction is equal to the centripetal force. Okay, the mass of attraction is equal to centripetal force. And don't forget that centripetal force is given by m okay, what do we call this? We call this angular velocity. So mass times velocity, then times your r is your what? Is your centripetal force. So if we equate this F to F, we have that what? G m all over what? R squared is equal to what? M omega 2 r. Okay, so this will take care of this. So if I want to make my m subject now, I'll say that my m, the mass of the sun, is now equal to, this one will go here to have, in fact, okay, don't forget that omega, we know the value of omega. Okay, we know the value of omega, and the value of omega is I think 2 pi over period. Yes, 2 pi over period. So if you put it here, we have, okay, but your omega is equal to what? 2 pi over period. So if you put it, you have that G capital letter M all over R squared is equal to what? 2 pi, in fact 4, okay, let me say 2 pi over period all squared. You have your R. Okay, so if we continue, we'll be having that G capital letter M all over R squared is equal to 4 pi squared R over what? Period. So if I make my M subject, I'll have what? 4 pi squared R cube. This time, this will give you R cube. Okay, all over what? GT. Okay, and then the period there is 1 complete year. The period we're going to use is what? 1 complete year. So I'll be having to get the mass of the sun, we'll be having we'll be having 4 times 3.142 all squared times 6,400 all raised to power 3, then over 6.7 times 10 raised to power minus 11 times my period there is a year, and the year is what? 365 days. 365 days times, converting it to seconds, it must be in seconds. So times 24 hours that make a day, times 60 that make a minute, an hour, then times 60 again that makes a minute. So 60 seconds make 1 minute, 60 minutes make 1 hour, 24 hours make 1 day, then 365 days make 1 year. So that is how to convert it to seconds. So if you do everything with your calculator, you'll be having 1.997 times 10 raised to power what? 30 kg. So the mass of the earth is less heavy than the mass of the sun. So the mass of the sun is heavier than the mass of the earth from the observation there. Okay, so the next thing we look at is acceleration due to gravity. Acceleration due to gravity. Acceleration due to gravity. Acceleration due to gravity. Now, okay, it said if a particle of mass m is on the surface of the earth, the force of attraction between m and the mass of the earth and the radius r is given by, you know that this is force is equal to what? G mass of the earth, then small m, the mass of a body on earth, is equal to what? All over what? R squared. So let me use capital letter R, radius of the earth. So we want to get acceleration due to gravity. So I know that my mg is force is equal to what? G m over what? R squared. So if this cancel one of these, so I have that my small g is what? G m over what? R squared. So if you put it, you have what? 6.7 times 10 raised to power minus 11 times the mass of the earth. We got it then as 5.997 times 10 raised to power what? 24. Don't forget, that's what we got there. All over what? 6,400 all squared. So if you do everything, you'll be having 9.87 meter per second square. So that is that. So that is why we always use that what? That G is equal to 9.8. Or we say approximately 10. Some people use approximately 10. So another thing you need to note is that acceleration due to gravity is we say that this is the value of acceleration due to gravity, and then note that the acceleration due to gravity varies with the height r from the center of the earth, okay, and is inversely proportional to the square of it. Okay, so another thing you need to note from here, you will see that what? You will see that acceleration due to gravity is inversely proportional to distance and then directly proportional to mass. Okay, so that is that. So I want to list out all the formulas before we start calculation. So the next thing we'll talk about is what? Gravitational potential. Gravitational potential. Gravitational gravitational potential. All right. They say that the Earth's gravitational potential at a position small letter r from the center of the Earth is the work done per unit mass with that will be done in taking the unit mass from infinity to that position r. Okay. First, the force on a mass m at the position r is given by this. So I know that first of all, I know that my F is equal to what? G m m all over what? R squared. Okay. So we want to calculate the work done. And don't forget that work done is what? Um, Work done is force times distance. Okay, that is work done. Work done is force times distance. So don't forget that work done is equal to what? Force times the change in the distance. Okay, work done times the force. So now, if you from this place now, I want to multiply this is equation 1. In equation 1, multiply by multiply equation 1 by the r. So if I multiply the two places by the r, I have that what? F dr is equal to what? G m m over r squared dr. Okay. So if we now have that now, we'll be having okay. So if we now have that, we'll be having that this is we have to integrate both sides. Okay, they say that total work done in moving the body from infinity to a position r um, is the potential at which is given by. Okay, they say that the potential, the work done is given by va, which is the potential difference, is given by va, or gravitational potential is given by 1 over m, the integral from a point in from infinity to a, of sorry, g capital letter m over what? Over r squared dr. So you need to know this, very very important. Okay, so now let us integrate to get the final answer. From here, we will now integrate to get the final answer. So now, remember that in integration, the r said that the only variable here is r. So every other thing is a constant. And according to integration, the constant can go outside. Then you now do your integration. So my va is equal to what? If this one goes outside, I have what? Gm m over this m that is here. Okay, I now have my integration from infinity to a of just 1 over, in fact 1 over what? R squared dr. Okay, so this is something that's saying this cancelling this, I have what? Gm, the integral of from infinity to a, according to indices, is r raised power minus 2 the r. Okay, and integration said add 1 to the power and divide by the new power. Add 1 to the power, divide by the new power. So if you have not watched my video on integration, please do that. It will help you to understand that. So I have my gm. Now if I want to add 1 here, I will have what? I have my r raised power minus 2 plus 1 all over the same minus 2 plus 1. Okay, that is how to integrate. But the integration has range. The range is from infinity to a. So I have what? This is my gm. What I have here is r raised power minus 1, then divided by minus 1. Then don't forget your range. Your range is from infinity to a. Okay, so anything divided by minus 1 shows that minus will come outside there. So if minus comes outside, or I now have, this is what? G m in bracket of minus r raised power minus 1. Okay, or let me just substitute. You know that is from infinity to a. So since it's from infinity to a, I'll be having substitute infinity then. So I substitute a, then minus the one infinity. So I have what? Anywhere I see arrow, I'll put my a. So I have what? A raised power minus 1. Okay, minus what do I have again? Put the next one. infinity raised to power minus 1, then everybody minus 1. Okay, so if you do that, and if this is 0, this minus this is this again, this divided by this is negative, so negative times this, I have what? Minus g m all over what? A, because this is minus, or minus g m, then a raised to power minus 1, so which is what? Minus g m over what? Over a. So that is what, and your A is distance. So let me use the radius of the earth here. So the gravitational potential will now be minus g m over what? R. So very, very important that gravitational potential, please, you need to know this formula, that the formula for gravitational potential is what? Minus g m over R. The formula for gravitational potential, V, is equal to what? Minus g m over R. Sorry, over the radius of the earth. Okay, so even if you don't understand this whole derivation, just know that what? That the gravitational potential is given by minus g blah 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 blah. So the next thing we'll talk about is what? Gravitational potential energy. Gravitational potential is different from gravitational potential energy. So let's talk about the gravitational potential energy. All right, now in the gravitational potential energy, we have that this one is very simple. The gravitational potential energy, you know that energy is work done, and work done and energy is empty. So energy is equal to what? The mass times what? The MVA. Just know that is what? The MVA, or MV. Mass times gravitational potential. That's all. The mass times gravitational potential. So gravitational potential energy is what? Gravitational potential energy. Let me call it the gravitational potential energy. Gravitational potential energy is equal to what? Mass, the product of mass times just potential energy. Potential energy. So we have that what? Our W is equal to what? M what? V. And what is our V? Don't forget, your V is what? Minus G M over R. So which is what? Minus G M M all over what? R. So that is that. That's the formula for your potential what? Gravitational potential energy. So that is that. So the next thing we'll talk about is what? Escape velocity. Escape velocity. Escape velocity. So escape velocity. They say that the potential energy of a particle on the earth surface is given by this. Don't forget, is given by this. Okay, so we want to calculate the, now if the body is turned up with a negative, with an initial velocity v, such that its kinetic energy is given by 1 over 2 mv square. Okay, so we want to calculate now the escape velocity. Now if you want to calculate the escape velocity, don't forget that work done and kinetic energy is the same thing. So work done is equal to kinetic energy. Kinetic energy. Okay? Or kinetic, let me use kinetic energy is equal to work done, is the same thing. So kinetic energy is equal to what? The work done. The work done. Okay? And then we have gotten the work done. You know that the work done is the potential what? Gravitational potential energy. That's what we are going to use. So I have the what? 1 over 2 mv squared is equal to what? My work done, which is this, is what? Minus g m over what? R. Okay, so I'm looking for my v. M will take care of m first. So my v squared will now be cross multiply. This one will go up. So I have minus 2 gm over what? R. Minus 2 gm over R. Okay, so if I now take the square root, I'll be having so if I now take the square root, I'll be having that my v is equal to what? The square root of minus 2 gm over what? R. Okay, the square root of minus 2 gm m over r. Okay, they say that if the body is turned up, okay, if the body is turned up, so we don't need the negative. So if the body is in reverse, okay, so if the body is in reverse, we don't need this negative. Okay, so it's gotten by this. So now we want to get the value. We want to get the value for the escape velocity of the earth, the mass on the earth. Okay, the escape velocity of the earth will give us the square root of 2 times 6.7 times 10 raised to power minus 11 times the mass of the earth. We got it as the mass of the earth gave us approximately 6. I told that some people use 6 or 5.997. So 6 times 10 raised to power what? 24, then divided by 6,400. So if you do everything, you have that what? The escape velocity of the earth will give you 11208 meter per second approximately. Okay. But this is the formula to calculate the escape velocity of any particle you want to calculate. But don't forget that from this place, I want to make the formula a little bit short. Okay, I know that my g, don't forget that we have that my escape velocity, where, don't forget that where v, please write somewhere that where v is equal to escape velocity. Escape velocity. Okay, don't forget that my v is equal to just the square root of what? 2gm over what? Over r. And then don't forget that your g is equal to what? Gm over what? R squared. Is it not true? So now if you do that, I want to replace now. Okay, watch what I want to put in my this thing. So the only problem here is that, okay, watch what will happen. I want to get the same thing here. So let me take one of the r here. So I have that what? G1 of the r is equal to what? Gm over r. That is multiplying everybody by r. All right, let me just show you what I just did. Multiply by r. Multiply by r. Okay, so I have what? Gr is equal to what? Gm over r squared times r. So this r will cancel one of these r. So I have that my gr is equal to what? Gm over r. So anywhere I see gm over r, okay, anywhere I see gm over r, I can put it as a gr. Okay, so what do I have now? That my v is equal to what? The square root of what? 2. Anyway, I see gm over r, I can present as g, so gr. Or let me use small letter r, so that we will not be talking about the radius of the earth. Okay, so that is that. So escape velocity is given by 2 square root of 2gr. Okay, escape velocity is given by square root of 2gr. So the last thing we're going to talk about here is orbitals round the earth. Orbitals around the earth, and then we are done with all the formulas we need. Then we'll now start solving calculations. Orbitals around the earth. Orbitals around the earth. Okay, they say that if a body circles the earth with velocity at a position r from the center of the earth, such that g is equal to mv squared over r, okay, and then which is equal to, okay, this we have that as long as the body has the velocity, the centripetal force equal this. Okay, okay, so they say orbitals around the earth. So we want to calculate the velocity of orbitals of any body that is around the earth. Okay, they say that is given by mv squared over r, that mv squared over r is equal to your gm m over r squared. So we now have that you cross multiply, you have that v is equal to this, take care of one of this, and this take care of this. So I have that v squared is equal to gm. So v will now be the square root of what? There is an r there. So our V will now be, okay, this one, we have 1 over 1 G down. So how do we get that? M, take care of M. Have 1 over M is, okay. So but if you want to bring in your G, it is G, GM over what? Over R. uh So, and I thought that GM over R is same thing as what? Small letter GR. And so that is that. So to calculate for the earth, I have that this is the square root of 9.8 times radius of the earth is 6,400. So if you get the square root of that, you'll be having 7,900 meter per second. Okay, so we are done with that. So let us now start calculation. So let's start calculation. Let me check my time. Okay, so let's start solving calculations. Okay, or maybe in the next video we solve calculation. Or do we solve it here? Let's just solve it here. The first question we're going to solve, example 1 said calculate the acceleration due to gravity, okay, at a height of 2000 kg above the surface of the earth. 2000 kg above the surface of the earth. Okay, want to calculate the acceleration due to gravity above the surface of the earth. Okay, we have that solution. You will start from your F is equal to what? G m over what? R squared. All right, but I know that my F is equal to what? Mg is equal to what? Your G m over what? Your R squared. Okay, so now this will take care of this to show that my G is equal to what? G m over what? R squared. Now, but they are talking about the radius here now will be added to the radius of the earth. The arrow I'm going to have here will be added to the height. Okay, so this is now GM over, instead of having just the radius of the earth, I have the radius of the earth plus that height. Just add the height to it, all square. That's all. You have gotten what you are looking for. So once they gave you height, so your arrow will now change to instead of normal the radius of the earth, you add it to the height where the body is. So what do we have now? Our G will now be, I know my G as what? 6.7 times 10 raised to power minus 11 times the mass of the earth. The mass of the earth is 6.0 times 10 raised to power 24. Okay, now divided by my radius of the earth is 6,400 plus at what height? At 2,000 height, all squared. So what do we have now? From here, we will now have that this is equal to, so do everything there, you'll be having your answer. There is no time to check time. Oh, the question has not even finished. Okay, so if you do everything there, you'll be having that the acceleration due to gravity there is what? 5.9 meter per second square. So this is the first question. So the second question said calculate number 2, calculate also the period of oscillation. Calculate also the period of oscillation of a pendulum of length 4 cm at this height. Okay, so this one is I, then 2II said compare this with compare this with the period on earth, and and hence explain if pendulum a pendulum clock taken up to that height will gain or lose time. Okay, so the first thing we calculated was our G. We have gotten our G, and I know that the period of oscillation is given by 2 pi the square root of what? L over G. Don't forget, the period of oscillation is given by 2 pi the square root of L over G. Okay, so they gave me that the length of that pendulum, where is it? Also calculate the period of oscillation of the length here. They gave me that the length L is equal to what? 4 cm. 4 cm. And 4 cm is 4 divided by 100, which is what? 0.04 meters. Okay. So for us to get the time now, the period is now what? 2 times 3.14142, then the square root of what? 0.04 over what? The G we got at that height is 5.9. So if you do everything there with your calculator, you'll be having the period is 0.526 seconds. Okay, so but the II said we should compare it with normal period on the earth surface. So when it is on the earth surface for II, so let us calculate the period when it is on the earth surface. I equally know that my period is equal to what? 2 pi the square root of what? L over G, which is what? 2 times 3.142, then the square root of what? 0.04 all over. The G here is normal acceleration due to gravity, which is what? 9.8. So if you do everything there, you'll be having that it is what? 0.762. You notice that what? The more you take an object high up, the more you taking an object to a particular height, the time reduces. Okay, the time reduces. The more you are going high, your time does what? uh Reduces. So or the time speeds up, because the period there is less than this one, so the time here is slow while the time here is very fast. Okay, so that is that. So when you take when you take an object to a particular height, what happens to the period? It speeds up. Which will give you small time. Right. So the next question we're going to calculate, another example. All right. Another example. Permit me to refill my marker before we continue. Okay. Another example they gave me here. They said uh, if a proton of mass 1.7 times 10 raised power minus 27 kg, okay, in a hydrogen atom is situated at a distance 5 times 10 raised power 11 meter from the electron. electron of mass 9.11 times 10 raised to power minus 31. Calculate the gravitational force. The gravitational force of attraction between them. Okay? Solution. The first thing they gave me is the first mass. That is the mass of proton. The mass of proton they gave me. In fact, sometimes they don't used to give the mass of proton. They will just tell you that the proton is attracted to the electron. So you need to know that the mass of proton is 1.7 times 10 raised to power minus 27. And then they gave me mass of electron, which is what? 9.11 times 10 raised to power minus 31. Okay? Kilogram. Okay? So kg. So the next thing they gave me is their distance. Their distance apart, r, is now 5.0 times 10 raised to power 11 meter. So I know that the force F is equal to what? G m1 m2 over what? R squared. So if you now have it, your G is always 6.67 or 6.7 times 10 raised to power what? Minus 11 times my mass. The first mass is what? 1.7 times 10 raised to power what? Minus 27 times the next one is what? 9.11 times 10 raised to power what? Minus 31 divided by what? 5.0 times 10 raised to power what? 11 all squared. So with your calculator, if you punch everything, you have that the force is 4.1 times 10 raised to power what? Minus 47 Newton. Okay? So that is that for that. So the next question. So question number 2. Question number 2 said, what is the gravitation? What is the gravitational force of attraction Gravitational force of attraction. Okay. What is the gravitational force of attraction between where am I? Between masses 10 kg and 25 kg, which are at a distance of 3.2 meter apart. Okay, at a distance of 3.2 meter apart. Solution. The first thing they gave me is my M1, which is what? 10 kg. They gave me my M2, which is 25 kg. And they gave me their distance apart, 3.1 meter. I know that my F is equal to what? G M1 M2 all over what? R squared, which is what? My G is always 6.67 times 10 raised to power minus 11 times my 25 times my 10 all divided by what? My 3.1 all squared. So if you punch everything you calculate, you have 1.63 times 10 raised to power what? Minus 9 Newton. Okay? So the next question, question number 3. These are very cheap questions. Question number 3. Question number 3 said, given that the mass of the planet Earth, they give you that it is Earth. The planet Earth is 6.0 times 10 raised to power 24 kg, and that of the moon is 7.0 times 10 raised to power 22 kg. They want to find the distance between them if the force of attraction existing between them is 1.8 times 10 raised to power 20 Newton. Okay? Solution. The first thing they gave me, F, is what? 1.8 times 10 raised power 20. The next thing they gave me is the mass, M1. The first mass they gave me is what? 6.0 times 10 raised power 24. The second mass they gave me is what? 7.0 times 10 raised power what? 22. Okay? And then I know that the radius of the Earth, R, is equal to what? 6,400 kg. Okay? So, okay, we don't need the radius of the Earth. So they're asking us their distance. What they're asking us is their distance. R is unknown. Okay, but I know that my F is equal to what? G M1 M2 over R squared. So if I make my R squared subject, R squared will now be what? G M1 M2 all over. This one will come down all over my F. So permit me to finish it up here. I'll have that my R will now be the square root of what? G M1 M2 all over what? F. So if you now put everything here, you'll be having your G is always 6.67 times 10 raised power minus 11 times your first mass there is 6.0 times 10 raised power 24. Okay, so we are still moving, times the next mass there is what? 7.0 times 10 raised power 22. Everybody over your force is what? 1.8 times 10 raised power 20. So press everything inside before you press square root. If you press everything inside, then you now press the square root. So you will now get that your answer is 3.9 times 10 raised power 8 meters. So that is their distance apart. Okay, so the next question, here said, question number 4 said, what is the gravitational potential of a body on Earth of mass 300 kg and radius 6.3 times 10 raised power minus 3, 6.3 times 10 raised power minus 3 meter. Okay, now solution. I told you that what? That V is equal to what? V is equal to Gm over R. That is your gravitational potential. So we have that what? My G, the first thing they gave me is my mass. The mass they gave me is 300 kg. Okay, and then they gave me R as well, 6.3 times 10 raised power minus 3 meters. So my G is always constant, 6.67 times 10 raised power minus 11. So I have, if I put everything, I have that my V is equal to 6.67 times 10 raised power minus 11 times my 300, then divided my 6.3 times 10 raised power minus 3. So if you do everything, you'll get that your gravitational potential is what? 3.2 times 10 raised power minus 6. I know that gravitational potential is work done, so it should be measured in joules. Gravitational potential is your work done and should be measured in joules. Okay, so the next question said, question number 5, and be number 6, said calculate the escape velocity. I gave you all this formula, so you should write it down and memorize it. Escape velocity of a rocket from the earth's gravitational field. From the earth's gravitational field, they say if the acceleration due to gravity is 9.8 meter per second square, okay, and the radius and the radius of the Earth is 6.4 times 10 raised power minus 10 raised power 6 meters. Okay, in this one self, they're not supposed to give you all this thing. They're supposed to tell you to calculate the escape velocity of a you should calculate the escape velocity of what? Of a rocket from the Earth's gravitational field. Once you know that it's from the Earth's gravitational field, you know that the G you must use is acceleration due to gravity, which is 9.8 meter per second square. Okay, and the R you are using is going to be the Earth. They're talking about the Earth. It's supposed to be the radius of the Earth, which is 6,400 kg, which is something as what? 6.4 times 10 raised power what? 6 multiplied by 1,000. You have times 10 raised power 6. Or if you multiply by 1,000, you have 6400000 in meters. So, and I know that your escape velocity, let me call it velocity, escape velocity, okay, is given by the square root of 2gr. Very simple formula, which is what? The square root of 2 times 9.8, then times 6412123. So if you do everything, you'll be having that the escape velocity there is 11200 meter per second. So that is your escape velocity. And don't forget that your velocity is measured in meter per second. Okay, so that is that for that. So the next question, question number 6 or question number 7, said a rocket of mass 120 kg is fired from the earth's surface, so that it just escape from the gravitational influence of the earth's field. Calculate the minimum velocity with which the rocket escapes. Okay, so we want to calculate the minimum velocity as which this thing escapes. Now they told you that it has already escaped the gravitational influence. Okay, so solution, I know that my v is equal to what? The square root of what? 2gr. Don't forget, I'm using this capital letter R because it's on the earth. 2gr, but don't forget that your g is equal to gm over what? R squared. Is it not true? So if you substitute g here, okay, let me use big R here, big R squared. Okay, if you substitute this g here, you have that what? V is equal to what? The square root of what? 2gm over R, because one of these R will cancel one of these R. So this is the formula I'm supposed to use. So this is equal to the square root of 2 times 6.67 times 10 raised power what? Minus 11 times the mass there. They gave me that the mass of that is 120, and divided by the radius of the earth is 6,400, or let me keep it in meter per second. So I'll be having another 3 zeros to it. Okay, so if you do everything there, you'll be having 5.0 times 10 raised power minus 8 in meter per second. Okay, in meter per second. All right, so the next question, said, question number 7 said, the radius of the moon is one fourth of the radius of the earth, while its mass while its mass is 180 184th 184th that of the earth. Okay, then I say what is the acceleration due to gravity? What is the acceleration due to gravity on the surface of the moon? On the surface of the moon, okay, comma, if the acceleration okay, we want to get the acceleration due to gravity on the surface of the moon, but they want to say if we don't even need this, is a bonus mark. Solution: just we want to calculate the acceleration due to gravity on the moon. Okay, we know that acceleration due to gravity, the normal formula for acceleration due to gravity is what? G is equal to what? Gm over what? Your r squared. Okay, Gm r squared. Now, but there's something they made, there's a statement they made here. They said that what? That the radius of the moon is one fourth. 1/4 means 1/4. Okay, 1/4 means 1/4. So if you have this, they say that the radius of the moon, let me call it r moon, is equal to what? 1/4 r 1/4 r radius of the earth. Let me call it re, or let me say 1/4 r, because r we know that is what? Radius of the earth. So I now have that okay, so which means that what? That 4r moon is equal to what? R. So which means the radius of the earth is 4 times the radius of the moon. Okay, we have gotten this, that the radius of the earth is 4 times the radius of the moon. So the next thing they told us that the mass of the moon, let me call it m. The mass of the moon is what? 1/84 times the mass of the earth. Okay, so which means the mass of the earth is 84 times the mass of the moon. So let us put everybody here, we get our answer. So I have that my G is equal to what? 6.6 okay, let's go. Okay, from here, watch, I want to show you something. We have that the acceleration due to gravity for the moon is equal to what? Is equal to, okay, we have Gm over what? R squared. So this is for my this is for moon and for moon. Then for the one for the earth, let me clean this because this is not the question for this, please, so that another person will. Okay, so I want to continue from here. I have that for the earth, G is what? Gm over what? Your r squared. Okay, but for the moon, G for the moon will now be what? Gm for moon all over what? R squared for moon. Okay, so now for this to be equal, we need to substitute everybody. Let me substitute everybody here and see what I'm going to have. If I substitute everybody, I'm going to have that my G for the moon will now be what? My normal G. Okay, but the mass of the earth will now change. Mass of the moon is 84 times mass of the earth. In fact, okay, I want to change everybody. G will change to G's. G's is this. The mass of the earth is 84 times the mass of the moon. Oh, how do I get this thing? I want to make it in a way that I will not put any value and then I will get my answer. I don't want to put any value, then I'll get my answer. Okay. So what am I calculating now? Okay. Ah, okay. From what I've gotten, they gave me this. Okay, so I know that my G now will now be what? My G times the mass of the Earth. The mass of the Earth, M, is equal to 84 mass of the moon. But I don't know mass of the moon. Okay, so which means I'm going to start from here in calculating it. Let me start from here. So G of the moon will now be what? My G of mass of the moon is 84 mass of the Earth. Where is it? 84 mass of the Earth. Where is the mass of the Earth? Okay, that is times what you times my M is what? 1. That is M over the mass of the Earth times what? 84. Okay. Now we have divide here. This two is what I've written. So divided by the mass of this one is sorry, the radius of this is 1/4. So I have 1/4, then that is r/4 all squared. Okay. I hope you got what I did here. Look at what I did from here. This is my G, or let me keep them. Let me keep them. Okay, you know that this thing is what? G times M, then divided by Rm squared, because this is over. Is it not true? So which is what? G times my mm is what? My mm is what? This is something as saying M/84. So I set as R/4. So I have what? M/84. Okay. Then divided by Rm is what? My Rm, where is Rm? My Rm is what? R/4. So normal R/4 all squared. So what do I have now? I have Gm/84 times this one will turn upside down. So sorry, 4 squared is 4 times 4, which is 16 over what? R squared. They turned upside down because I've changed division to multiplication. So I will now have that this is what? My Gm I'm looking for is what? This and this. 16/84 is my constant I have. So I have my Gm over what? Over R squared. And I know that normal G is equal to what? Gm over what? R squared. So instead of writing this thing, I will now write that this is 16 over what? 84 G. Okay, which is what? 16/84 times G is what? 9.8/1. So that is what, because I don't want to put any value. So I want to, this is 16 times 9.8, then divided by 84. So I now have that the acceleration due to gravity there is 1.87. Okay. Where is it? 1.87 meter per second square. So that is that. Okay. So the next question, which is the last question I'm going to solve, the next question, which is the last question I'm going to solve here, said, that's number 8 question, said an object having a mass of 25 kg on Earth is taken to a planet where the acceleration due to gravity is one half of, one half means 1/2, okay, of its value on Earth. Then what is the mass? What is the mass of the object on that planet? Okay. So from here, I know that my G is equal to what? Gm over what? Your R squared. Okay. Gm over r squared. Now, this shows that that g G is directly proportional to what? To m. So G is now Km. Okay, so my K will now give me G over m. So which is what? G1 over m1 is equal to what? G2 over m2. Okay, G1 over m1 is equal to G2 over m2. Very important formula to note. So let me finish it up here. So they gave me that the mass m1 is equal to 25 kg. I'm looking for mass m2, which is the mass on that planet. This one is mass on the earth. Okay. So but I know that g on the planet, g1 is just g1. Or you can use 9.8 if you want. Let me use 9.8. 9.8. Okay, then my g2 they said is half of this. That is 1 over 2 g1, which is what? 1 over 2 times 9.8, which is what? 9.8 divided by 2. 9.8 9.8 divided by 2. So I have 4.9. Okay, meter per second square. So you now have that your what? Your from this formula, I want to make M2 subject. So to make M2 subject means this one will go up, this one will come down, this one will go up. So I have M1 G2 all over G1. Okay, if you cross multiply first, then you make it subject. So my M2 will now be, my M1 is 25 times my G2 is 4.9, then divided by 9.8. Okay, so if you now do that, you have times 25 divided by 9.8. So I have 12.5 kg. Okay, so 12.5 kg, that is half of it. So thank you very much for watching. Please like, share, and subscribe. Share to anyone that needs it.